Good morning, algebra. So we are going to continue looking at these new types of patterns, and we're going to give them a name today. So we're going to name this pattern a quadratic function or a quadratic relationship. And basically what quadratic means, and you'll see it throughout the lesson, we'll see it thrown around in words. Quadratic, well, if you look at the word, you see quad, like quadrangle, or the thing you ride that has four wheels. And quad is the word for square, basically. So you might be thinking, all right, well, that has to do with like the number 4. But really what it has to do is taking a number and squaring a number. So we're basically going to be looking at patterns where we have to square numbers. So like our patterns are going to involve x squared today. All right, and unless a lot of them yesterday and previous days also involved that. So we're sticking with that same vein. And just whenever making patterns, think about how would an x squared fit into this. All right? Okay, so our first activity, it's really not a warm-up. I don't know why they thought it was a warm-up. But basically, we have 3 figures. We have figure A is a large square. And figure B is a large square with a smaller square removed. And figure C is composed of 2 large squares and 1 smaller square added. So, I want you to take some time to try to fill out whatever you can of this table. Some of it should be easy, and some of it will be difficult, and some you may not be able to do. But write an expression to represent the area of each shaded figure. So not the white taking out bits, just the shaded parts. All right? So again, for some of them, it should be easy. Don't say I can't do it. Some of them are easy. And some of them are a little bit more difficult, all right? And some of them you won't be able to do it all. So do whatever you can, and then continue with the next part of the video. So at least the pieces of these should have been reasonable to deal with. So the side length is 4. The area of square A, 4 by 4, is just 16. So that's what 16 comes from. Area of B, well, that's just the 4 by 4. That's just 16, but taking away 1. That little piece there is 1, so we're just subtracting 1 here. And then for the large one at the end, we have 2 of the 16s. So 16 plus 1. Or really, the better way of writing it is we're going to write things with multiplication, really, because it's easier. Well, not easier, but it just, mathematically, it looks simpler. That's just more standard. Because with larger expressions like down below, it takes up less space to show multiplication. So 2 times 16 plus 1. Or you could just write 33. All right, so now if you get to x. If the side length was x, well, x times x is x squared, so the area would be x squared. The area of B is x by x, but you're taking out that 1, so it would be x squared minus 1. And then for C, the side length is still x, so x squared plus 1, which gets me 2 x squareds and a 1. All right, so that x squared plus that x squared gets me 2x squared. All right, because again, these x squareds are like terms. They can be combined. If I have 1x squared and another x squared, that gives me 2x squareds, which is what this is. I have x squared and x squared combines gets me 2x squareds. And then if my side length was 4x, if it was 4x, then I'd say, all right, well, one of those boxes was 16x squared. It says 4x times 4x. Now notice here I can multiply the coefficients and I multiply the x's. So 4 times 4 got me 16, and then x times x got me x squared. So we have 16x squared for the first one. And then if my side length is 4x, then this box with 1 taken out the middle is 16x squared minus 1. And then that right box over here, I have 16x squared plus 16x squared plus 1. Or it's really 16x squared times 2 plus 1, which is just 32x squared plus 1. Now the last one's a bit trickier. So if you don't know the last one now, like, that's fine. You might have figured it out. But that one's definitely more of a challenge. And if we were in the classroom, I would probably debate talking about this one quite yet. But since we're here and, well, I can't hear you yelling at me and groaning at me for doing this one, we're going to give it a try. So really what I'm going to do for this one is I'm going to redraw the square down here. I'm going to draw the square down here and hope it helps to make sense. Because when you learned to multiply numbers like 12 by 15, you might have learned to multiply them in a similar way. So basically I have a square and the side length is x plus 3. So really I can break up the square into an x by x and then add on 3 and then add on 3. And I can find the area of each of these little pieces. So I have an x plus 3 and an x plus 3. So now this square right here, the x by x, is really x squared. And this one over here is really 3 by x. So it's 3x. This one here is x by 3. So that one's 3x. And this one down here is 3 by 3. So it's 3 times 3. So really my whole square is x squared plus 3x plus 3x plus 9. And I have some like terms here. That gets me x squared plus 6x plus 9. All right, and then over here, it's the same thing for figure B, but figure B, it's the same square, but we're taking out that 1. Sorry, so it's whatever I had for the previous square, but minus 1. Minus 1. Or that would just look like x squared plus 6x plus 9 minus 1 is 8. All right, and then last one over here. Sorry, my phone is casting a shadow. Okay. Last one over here, I got the 2 boxes and then the 1. So I have to add 2 of these together. So x squared plus 6x plus 9 plus x squared plus 6x plus 9 plus 1. So all right, here's a lot of like terms. X squared, 2x squared, 6x, 6x is 12x, 9 and 9 and 1 gets me 19. All right, so there's that. If you didn't get the blue ones, like seriously, don't worry about that much. We should have hopefully been able to reason out this one and the rest from that. If you didn't get it, obviously don't worry about it. We got a ways to go before we're gonna be awesome at this. All right. So on the back, we want to take a look at another type of geometric pattern. And again, we're thinking about quadratic. We want to get used to that word quadratic. Again, thinking of quad, squaring, something with an x squared. So we're thinking about what is being squared here. So if the pattern continues, what will we see in step 5 and step 18? So first of all, before you even do that, think about what pattern you actually see here. Take a moment to pause the video. What do you actually see as being the pattern here? What's the same and what changes? All right. So I'm seeing that these 4 outsiders, they're always the same. I've always got 4 on the outside. So if I have step 5, or I'll do step 4 first, why not? I'm gonna have those 4 on the outside, and oh goodness, please bear with me. And then inside, what's going on? What am I going to see? I'll start step 5 too, while you think about what's going on the inside. So what's going on the inside? All right, so here we have 1 square. Here we have a 2 by 2. And here we have a 3 by 3. So we're adding length and width to these. So notice, it's step 1, it's a 1 by 1. At step 2, it's 2 by 2. Step 3, it's 3 by 3. So what we really have is an x by x. So I'm going to make this 4. Cool, 4. And I'll make this vertical one 4 as well. So let's see, half and half again is 4. All right, cool. That's acceptable. All right. That's pretty okay. So there's our step 4. It's a 4 by 4. It's 4 by 4. And step 5 is going to be a 5, it's going to be more difficult, by 5. Let's see, I'll cut off an end. I'll do the rest in half and half again. Cut off an end and half, oh dear, and half again. That's not bad. I did pretty good. All right, so we got a 4 by 4 and a 5 by 5. So really, going to, so we have a pattern now. We have an x by x and a starting out 4. So sketch or describe the figure at each steps. Step blank has a blank by blank square. And in the previous day, you guys got confused by like the nth step. We can call it the nth step. Step n has an n by n square and 4 additional squares. At the corner. So step 5 is going to have, let's see, 5 by 5 plus 4 is going to be 29. And then 18 is going to have 18 times 18 plus 4. So 18 times 18 is 324 plus 4. So it's going to have 328 squares. And I know because of my rule. So we can write an equation now. Instead of 5 times 5 plus 4 and 18 times 18 plus 4, we want to think about, like, all right, the number of squares as a function of n is going to be, well, not 5 times 5, it's going to be n times n, or n squared plus 4. Because really I have n times n plus 4, which is really just n squared plus that original 4. And that works for all of them, right? Step 1, 1 squared is 1, plus 4 is 5. Step 2, 2 squared is 4, plus 4 is 8. 3 squared is 9, plus 4 is 13. And you see geometrically where that n squared is. The n squared is the blue, and the green is the plus 4. So that's really where that whole thing is coming from. We're visually seeing what this pattern is. All right. So, let's do a different one. Well, same pattern. But now for the original step in the step pattern in the statement, write an equation to represent the relationship between the step number and the perimeter. So let's get a new color. Let's use pink for perimeter. Actually, no, I use purple for perimeter. That sounds even better. Yeah, purple. So, purple for perimeter. So, I'm going to go ahead and draw step 1 again. Oh gosh, I don't know why I'm doing this. So, I'm going to go ahead and draw step 1, 2, 3, and 4 and come back to you. Okay, so I've drawn all 4 of these, and I know I have no room to write the equation now, but that's okay. It's important to look at the math first. So, let's look at the actual perimeter. So, we have step 1. So my perimeter outside, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I lost count. 20. Yeah. I say our perimeter is 20 for step 1. All right. Step 2. Our perimeter is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay. Wait, is that even right? No. 4, 4, 4, 4, 16. It's 24. Roboto, come on, 24. All right, so I'm starting to notice where's the perimeter changing. What is actually causing the perimeter to change? So here, again, we have 1, 2, 3, 4. Each of the 4 on the outside are staying the same. We always have these 4 are on the outside. 1, 2, 3, 4. 4, 4, 4. And that's 12. So how's my interior perimeter changing? My interior went from a 1, 2, 3, 4. That interior went from 4 to 1, 2, 3, 4, 5, 6, 7, 8. Now it's at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Interesting. This isn't going to be quadratic at all. So this one, I'm going to guess, is going to be 4, 8, 12, 16. And those outside 4 are still going to say is 4, 4, 4, and 4. So my perimeters are 28 and 32. So how is my perimeter changing? Is it quadratic? Is it exponential? Is it linear? It's actually linear. It's going up constantly. I'm going up. I'm adding 4 to my perimeter every time. Because if I'm adding 1 to each dimension, it looks like I'm adding, like, okay, I'm adding 1 to the right, 1 up and down, 1 to the left, and then 1 up and down again. I'm adding 4 boxes around the outside to measure. All right, so my rule is going to be y equals 4x plus something. What's my y-intercept? It's not 20. Let's see, 4x, 4 times 1 is 4. It'd be 4x plus 16. Because 4 times 1 is 4, plus 16 is 20. 4 times 2 is 8, plus 16 is 24. 4 times 3 is 12, plus 16 is 28. 4 times 4 is 16, plus 16 is 32. So that'd be my rule there. But really noticing, we're not necessarily dealing with quadratics all the time. We're actually looking at this perimeter would actually just be a linear type thing. Only two-dimensional. All right. So let's sketch the first 3 steps of a pattern that could be represented by the equation n squared minus 1. Take a minute to think about what that might look like, because it might look different for you than it will be to me. All right. So you want to do a step 1 for n squared minus 1, a step 2, a step 3, and a step 4. All right, give it a try. So let's think back. This example from figure B actually was very similar. It was x squared minus 1. It was the dimensions minus 1. So this actually was very similar. You could have done like a figure that had a little piece cut out right here. They're very similar examples, a 1 by 1 cutout. What I thought about was, well, I could do that 1 by 1 square and then erase one of them. So I'm getting rid of arbitrarily the lower left squares. That first one's got nothing there. Second one, I did a 2 by 2, erased that one. Third one, did a 3 by 3, erased that one. Fourth one, did a 4 by 4, and erased that one. We could have done something similar. You could have erased just any random one. You could have had that cutout type thing. But the goal is recognizing that this is a square, and this is just getting rid of one of those squares. All right? So hope that wasn't too crazy. We got a little bit left for today. This one, hopefully you can do by yourself. Think through by yourself. So we got this pattern right here. We got step 1, we got step 2, and we got a step 3. So notice what's going on here. Try to sketch the next few steps. This is really the part where you're going to pause, and I'm not going to tell you how to do it. We're just going to pause it for a nice long time, and we're going to just be given the answers at some point. So sketch the next few steps. So that shouldn't be too bad. You can see what's happening, how it's changing. Do you agree or disagree with Peyton that the number is growing linearly because this reason? And then to represent the number of steps, 2 kids actually wrote rules. See if these rules follow along. And if you think they do or don't, try plugging in. You already know what f of 1 is, and you already know what f of 2 is, and you already know what f of 3 is. So figure out, do those things actually get you the right numbers? All right, give that a try before we just get the answers, all right? So here's my next few steps for our pattern. I just realized you add 1 to the width, and you add 1 to the height every time. So here my width was 1, height was 3, 1 by 3, 2 by 4, 3 by 5. So that's going to be a 4 by 6 and a 5 by 7. And then I wrote them algebraically. I noticed that the width in pink was always the step number, and the height was always 2 more than the step number, x plus 2. That's going to come in handy more for question 3. So here's the shapes. You just count the boxes, and you realize you have 3, 8, 15, 24, and 35 boxes. So Peyton was incorrect. Width grows linearly and length grows linearly, but if you combine those two, you realize that area does not grow linearly. Area actually grows quadratically. So that's because we are squaring something. And you can see it grows quadratically because also the amount you're increasing by is actually going up linearly. So the first time we added 5, then we added 7, then we added 9, and then we added 11. And if that growth is linear, if the change is linear, then you have quadratic. I know it's kind of confusing, but if the change is linear, you have quadratic. And fun fact, if the change of the change is not linear, but the change of the change of the change is linear, then it's a cubic function. But you'll get to those much later, don't worry. That's just a fun fact that you can sort of learn in calculus, but who cares? Okay. To represent the number of squares, after n steps, Oliver and Shannon wrote different equations. Amazing what you can get done when you're not talking to each other in class. And they wrote this. They wrote this, n times n plus 2 for Oliver. Does that work? Well, I noticed if n is 1, then n plus 2 is 3, and that got me 3, 8, and 15, so it seems to work. And if I follow Shannon's method of n squared plus 2n, n squared when n is 1, I have 1 plus 2 times 1 is 2, which gives me 3. 2 squared is 4, 2 times 2 is 4, 4 plus 4 is 8. 3 squared is 9, and 2 times 3 is 6, so 9 and 6 gets you 15. So it seems to me that both work, and yes, they both are going to be models for this. And I kind of the same thing up here, where like the width was x, and the length was x plus 2. So area would be x times x plus 2 for all of these cases. And yeah, if these are the same rule, because if you do n times n plus 2 and you distribute that n times n is n squared, and n times 2 gets me 2n. So it's really just distributing, which is probably how Shannon got her equation in the first place. Unless she was thinking about it like, well, I have that 1 square and then 2 times 1 above, or I have a 2 by 2 and then a 2 by 2 again. Like I have 2 is always my length of the thing above the square. There's always a 2 length up there above the square. Sorry. A 2 length thing above a 1 by 1. A 2 by 2 square and then a length of 2 above it. A 3 by 3 square and then a 2 by 3 rectangle above it. So you could have also thought about it like that. All right, there's a lesson for today. Hopefully the patterns in your exit slip go pretty well. So best of luck with that.